Greetings, fellow time travelers, or perhaps future time travelers, or maybe just curious minds exploring the fascinating, mind-bending possibilities of a journey through time. Today, we're diving headfirst into the physics of time travel, a subject that has captivated scientists, science fiction writers, and anyone who's ever wished they could relive a moment or peek into the future. But is it merely the stuff of dreams, or is there a sliver of scientific possibility lurking beneath the surface? Let's start with the basics. We experience time as a linear progression, a one-way street from the past, through the present, and into the future. But Einstein's theory of relativity throws a cosmic wrench into this seemingly simple equation. Relativity tells us that time isn't absolute. It's relative to the observer and their speed and gravitational environment. Imagine two clocks, one on Earth and one on a spaceship traveling at near light speed. The clock on the spaceship, due to its incredible velocity, will tick slower than the clock on Earth. This isn't just a theoretical quirk. It's been experimentally verified using incredibly precise atomic clocks. This phenomenon, known as time dilation, is a fundamental aspect of our universe and a cornerstone of any discussion about time travel. But time dilation alone isn't sufficient for the kind of time travel depicted in our favorite science fiction stories. We're talking about hopping into a machine, setting a date, and arriving at your destination in the past or future. That requires a more radical approach, and that's where wormholes come in. Imagine spacetime as a fabric, a vast, four-dimensional expanse. Wormholes are hypothetical tunnels through this fabric, shortcuts connecting distant points in space and time. Think of it like folding a piece of paper. Instead of traveling across the surface, you punch a hole through it, creating a much shorter route. Now, the catch with wormholes is that they are purely theoretical. We have no direct observational evidence of their existence. Their theoretical existence relies on exotic matter, a substance with negative mass energy density. This is matter that would exhibit repulsive gravity, the opposite of what we observe with ordinary matter. While exotic matter is a theoretical possibility, we've never observed it, and its properties are still largely unknown. So, while the concept of wormholes as time travel portals is tantalizing, the practical challenges are, to put it mildly, monumental. Another intriguing avenue for time travel exploration lies within the concept of closed timelike curves. These are theoretical paths in spacetime that loop back on themselves, allowing for travel to one's own past. Imagine a circle in spacetime. You start at a point, travel along the curve, and end up back at your starting point, but at an earlier time. Mathematically, CTCs are possible solutions to Einstein's field equations, but their physical feasibility remains highly debated. The main obstacle is the potential for paradoxes, most famously the grandfather paradox. If you were to travel back in time and prevent your own grandparents from meeting, you would cease to exist, thus preventing your journey to the past in the first place. This creates a logical contradiction that has plagued time travel theories for decades. However, some physicists propose solutions to these paradoxes. One suggestion is the many worlds interpretation of quantum mechanics. This theory suggests that every quantum event creates a branching universe, meaning that when you travel to the past, you're not altering your own timeline, but rather creating a new one. In this new universe, your actions in the past would have different consequences without affecting your original timeline. This is a fascinating concept, but it's still a theoretical interpretation of quantum mechanics, and its implications for time travel are still under intense scrutiny. Let's not forget about the energy requirements. Traveling through time, whether via wormholes or CTCs, would demand unimaginable amounts of energy. We're talking about energy levels far beyond anything we can currently harness. Even if we could theoretically manipulate spacetime, the energy needed to create and stabilize a wormhole or navigate a CTC would likely dwarf the total energy output of our sun. This presents a practical hurdle that may be insurmountable, at least for the foreseeable future. But what if we shift our focus from macroscopic time travel, the kind involving human beings and sophisticated machines, to the microscopic level? Quantum mechanics, with its inherent uncertainties and probabilities, offers some intriguing possibilities. Quantum entanglement, for example, where two particles become linked regardless of the distance separating them, might offer a glimpse into non-local interactions that could, in some theoretical framework, be exploited for temporal manipulation. However, translating this microscopic entanglement into macroscopic time travel remains a vast, unexplored territory. Another aspect to consider is the impact of time travel on causality. Causality is the principle that cause must precede effect. Time travel, particularly to the past, poses a direct challenge to this fundamental principle. The potential for paradoxes, as we've already discussed, highlights the complexities and inherent contradictions that arise when contemplating the possibility of altering past events. Understanding the implications of causality in a universe that allows for time travel is crucial for any serious consideration of its feasibility. The pursuit of understanding time travel is a journey through the deepest mysteries of the universe. It's a quest that blends theoretical physics, mathematics, and philosophy in a way that few other scientific endeavors can match. While the technology required for time travel remains firmly in the realm of science fiction, the theoretical groundwork laid by Einstein and others continues to inspire and challenge our understanding of space, time, and the very fabric of reality. The journey itself, the exploration of these ideas, is as fascinating and rewarding as the destination might ever be. Perhaps one day we will unravel the secrets of time travel, unlocking the ability to journey through the temporal landscape. But until then, the very act of exploring these concepts pushes the boundaries of human knowledge, forcing us to confront some of the most fundamental questions about existence itself. The pursuit of time travel, whether achievable or not, serves as a powerful reminder of the boundless curiosity and ingenuity of the human spirit. And that in itself is a journey worth undertaking. So keep looking up, keep questioning, and keep exploring the incredible mysteries of our universe. The future, or perhaps the past, may hold more answers than we can currently imagine.